Recording. Okay, thank you. So we have the usual flow is like that. So the usual flow is in the program. What a program does, whatever your programming language is, stay in the program, stay in the same stack, same code, so instruction pointer switches in some area, and that's it. And in the last week, we talked about this program A, program B. That we talked about different ways of changing this behavior. So we will have such changes. So the CPU changes the state from program A to program B. So we have loops, jumps, function calls, and non-local jumps staying in the same boundary, quite conservative in the same program. But now we are jumping to another program. And this is called context switch. And today I'm going to show you some examples of that. So this is our first way. The second way is to get the operating system versus program. When I was an undergraduate student, I thought that the operating system is like a service. So if you, the operating system reads your program, gets the next instruction, execute that. Operating system fetch the next instruction, execute that. So it was a wrong idea I had. In an actual system, so this is some sort of emulation. So if you have a CPU emulator, it works like that. Okay, emulator fetches the instruction and executes the instruction. But in operating system, it is native. Even in the virtual machines, it's native code. That means CPU belongs to the program. So when your program is executing, it is executing in the bare metal. It is not some service. There is no interaction between the operating system when you are number crunching. Okay, adding two numbers, multiplying two matrices. Operating system doesn't know, doesn't care about it. However, we have many programs and many services in the operating system. So operating system has to do some two basic tasks. One is the hardware operations. Okay, so your hardware doesn't wait for you. Your hardware doesn't wait for your program to terminate, multiply matrices, whatever you are doing. You cannot make CPU busy when there are millions of bytes waiting in a queue to deliver the message to you, especially in network cards, etc. Speed requiring devices, you need that, so you cannot delay it. So what you have is, we have hardware interrupts. So in this second case, your program 1 is executing peacefully, and a network packet just arrives. Sorry for my writing. This is the best I can write. My writing is worse even in the board. So when a network packet arrives, so operating system should take care of that. So your kernel has to intervene, execute some code, and go back to the process 1. And this is called interrupt service routine. Okay. Kernel is kernel a process? No, it is not a process. Kernel is actually, you will have a better idea after this hour what kernel is. Kernel doesn't own the system. Actually, CPU should belong to the programs. Kernel is the orchestrator of what's going on. Actually, you can consider in two ways. It's like a zebra, okay? Is zebra black stripes on white or white stripes on black? Okay, so there's this controversy. Okay, it is something like that. Operating system has the CPU and lets processes run, versus processes have the CPU and eventually operating system intervenes. Both are correct, both are wrong. This is the interrupt case. The process is happily executing and some hardware event occurred and it is handled and go back to the process. And this is an interesting boundary. And this boundary is the user space versus kernel space. So this is another boundary. The third case is actually, in order to be fair and in order to time share, so for time sharing, kernel intervenes by using, again, an interrupt, but the interrupt is not some external hardware triggered interrupt, but it is what. So when there are timely events, which interrupt I am talking about? Do you have a hint about that from last week? Yes, Ulaş Şahin, timer interrupt. So it is again a hardware interrupt, but it is not some remote triggered operation, but it is adjusted by kernel. So we have a timer interrupt, so that kernel can periodically intervene what's going on, and what we can call housekeeping here. I couldn't write housekeeping, sorry about that, but it is housekeeping operations. And most important operation is scheduling. So taking CPU from P1 to P2. I'm going to give better examples later. And the fourth operation I'm going to talk about, actually there are names for that in your slides, exceptions, etc. But at the end you will see they are all interrupt based. This is something interesting. And fourth one is about our timer interrupts shifted after hardware interrupts. There is no shifting, but there is something we call interrupt priority. And based on priority, the interrupts can intervene each other and so on. So we can have non-maskable interrupts and maskable interrupts and reoccurring interrupts. There are varieties provided by the underlying hardware and the organization of the computer. And in the operating system adjusts them based on their priority and so on, how they are important and so on. And interrupt service routines are very short so that they will not step each other's foot, okay? So the answer is, if your hardware interrupt handler is masking interrupts for time being, and then unmasking it during that period, no other interrupt can be handled. They are only set as a flag, okay? So they wait as a flag. So it is yes and no based on the priority of the interrupts you are talking about. And the kernel designers try to make it minimal, only one. So the masking interrupts minimum, okay, so that everyone can execute happily. The fourth one is about user space requesting something from kernel. Okay. We ask questions to kernel, and last week, you have seen it as system calls. Okay, so this is the fourth one, the system calls. And I'm going to show you these mechanisms today. First, let us start from okay, so now first let me show you some evidence for the context switch. I had used some graphs of a working system. I believe this is okay. Can you see it? So this is not the correct one. So this is more impressive picture. I think you cannot understand what's going on, but in the left-hand side, you see the processes. And this timeline is just 10 seconds of my desktop having context switches. And let me just zoom so that you can understand what my CPU does by that time, okay? There might be some small errors, but the idea is CPU belongs to this process during this interval, then this process, then this process, then this process, and so on. My machine is multi-core machine, so you can have overlaps. But the idea is my CPU does this many context switch in this half a second period, okay? So this is how CPU timelines versus the acting process changes. I have a easier to understand example, which is, hope I can find it. So this is a better, not better, but the smaller program. There are two programs in the system, P2 and P1. One basically tries to crack a password, something like that. So it is a CPU intensive task. Doesn't do any operation, but printing something eventually. And the other one sleeps for a while. The P2 sleeps for a while, then do some silly number crunching job. So let me just show you one period in this example. So this is the sleep interval of my CPU. By the way, this is a virtual machine, and there is only one CPU in this one. So this is my sleep period. So P2 and P2 versions, two instances of P2 are not working here. And during forget about perf, which is just taking this output. So during this period, as you can see, we can have writes of, sorry, not write, but the CPU belongs to P1 and P1. And then during this period, CPU belongs to P1, P2, P1, P2, P1, P2, then goes back to P1, P1, okay? So actually I had a better one, but I couldn't find it. I will not this one. This one. Okay, this one. Okay, there is no perf here, and system calls are not here, so that's why we can have a better picture of this one. As you can see, during sleep periods, sorry, this is the sleep period. This area is empty. I have P1, 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 then P1, P2, P1, P2, P2, P1. The order is determined by the scheduler. And in 10 seconds, you can see how much context switch my system does. And this tool is just marking the context switches. In some intervals, we can have other processes intervening, but most of CPU is used by those. So this is example of context switch. Now, turning back to the presentation. So return back to here. Now let us see what context switch is like. So the idea is, what is, so let me ask you a question. What is the CPU context? By the way, in the other screen, I cannot see your questions. Hocam, I/O intensif olan bir proses CPU almadan I/O işlemini yapabilir mi? It cannot start the I/O operation because I/O operation is a system call. So in order to start it, it needs to take the CPU. Yes, but I/O operation actually takes place later. The running process plus current information in CPU, data in the registers, every information about CPU. What do you mean by every information? So I am talking about CPU context. What is CPU context? So it is like when I freeze time, what you like to save for your CPU. Next instruction, data in registers. So registers as important keyword here. So it is like I just take a snapshot of CPU, plug CPU out, and I install a new CPU. What should I preserve in the CPU? Forget about cache and memory related things, main memory related things. CPU's current state is actually registers. Okay. The registers there are many registers, but actually 2 of them are crucially important. Actually 3, but you should know about, in terms of CPU context, 2 are very important. What are they? RSP, RIP. Okay, the stack pointer and the instruction pointer. Why? Because one said next instruction to execute, and the second one says when we return, which function we are going to go, or which are our local variables, and so on. So in this scenario of, so the idea here is, in the context switch, I'm going to have process 1 context is currently active. So we have instruction pointer of 1, stack pointer of 1, and all other registers belonging to 1 is active at this time. And then something happens. That something is a timer interrupt. And I don't know what happens, but later I'm going to have this process 2 context is active. Instruction pointer 1, stack pointer 1, and registers. So what's going on here? So I make an interrupt. Usually interrupts are handled in the stack, in the same stack as the process, or in a different stack, the kernel stack. So this is my interrupt service routine activation record. It enters the stack and start executing some code. So here I have P1 in the stack. And whatever happens, I don't know what happens, but when I execute return from interrupt instruction, I will have P2 in the stack. And the registers are recovered as the register set of process 2. Okay, so this is 2. Okay, So this happens in a context switch, and it is actually a little bit time-consuming operation. And what really happens is, during this period, the stack is adjusted by kernel. So kernel modifies the current stack so that it is going to recover the previous stack pointer, and so on. And most importantly, memory address space. Switch to P2. Okay, and this is the context switch. So why context switch is expensive? Any idea? CPU is busy doing the context switch. CPU is used by the kernel because uses main memory. You are getting close to store the old program states. Okay, well, the program state takes some kilobytes, so it may get some kilobytes, but it is not done through whole copy operation, but just a pointer redirection, so it is not that expensive. The register set is copied. Okay, so register set is taken from problem main memory into register set, and register set to the main memory. It's one source of cost, but it is not the most important one. Okay, we need to stop all process. Actually, the kernel is executing. If you have multiple CPUs, the other CPUs doesn't have to stop. Goes back and forth instead of working process. Think of it about memory. The memory is the keyword here. And actually, it is related to a little bit of memory security. Your process 1 belongs to me, and process 2 belongs to one of you. The process 2 can process 2 access the memory information of process 1. Yes, you get close. Cache and locality. Possible page fault. Yes, you're getting closer and closer. The idea is I have to invalidate the cache. All cache entries of P1 should be invalidated, not the memory cache, but the address translation cache. We are going to talk about that later. We have to invalidate that so that the user, the next user, cannot access the memory area of the previous user. Okay, so I invalidate all of the address translation cache. So I will start from a new address translation vector. As a result, all of the following memory requests will be page faults up to some moment. Okay, and this is one of the crucial parts of the context switch. Cache is actually the already stored in the main memory. You just invalidate that so that all of the following came from main memory. So you lose, and the following address translation, you lose this speed up coming from the cache. So let me just draw here. So P1 has some cache entries, address translation, and then you make context switch. So these entries belongs to 1. So it makes cache invalidate. So now my cache is clear. Now new process P2 starts executing, and P2 asking for some memory address. And the question is, since cache is empty, it is coming from main memory. Okay, it's coming from main memory, filling one entry here. The next request coming from main memory, filling another entry, and it goes like that. So for some milliseconds of time, not milliseconds, even microseconds of time, we are using memory from main memory, not the cache, address translation memory. So that's why this some early stage of P2, we have memory operations slow, and this is the main point we are losing. Okay, is it clear? Yes, both security and also validity of operation, not only security. The process one is using some pointer A, and in process two, that pointer address is empty. It should provide segmentation fault. But in process one, it is legal. If process two makes that instruction access, it should be illegal, but it will work as if it was legal. So it is also about the validity of your actions. Hocam page fault main memory'de bulunmayınca mı oluyor? Yes. Yes, it is. It is even not in the main memory. Page fault says that. The address you are looking is not in physical memory yet. There are two options. Either it is illegal completely, so you should have taken the segmentation fault, so the page fault is the early stage of segmentation fault, or it is recoverable, so you can fill some data, so you know a way of recovering that. The page fault is the way of recovering the data. We are going to talk about that in the 4th chapter, I believe. Okay. What could happen if you don't invalidate the cache? As I said, you might have taken invalid actions as if they were valid. So you should take segmentation fault. You will get some garbage as a result. Also, the security, of course, you can access my data. Even in this secure cache invalidation, because of some CPU bugs, we had some data leakage. You heard about meltdown and some similar CPU errors. Any of you heard about that? They were related to that. If you probe cache properly, you can access previous person's information. So statistically, for example, you can set 1 million requests, and depending on the failure rate, you can understand which byte is over there, and so on. Okay, so this is out of our scope. So this is basically what happens during the context switch and what happens through this interrupt handler. Now I would like to talk a little bit about system calls. So the timer interrupt and the regular hardware interrupts are not much different, but the system calls are completely different scenario. And the requirements for system call is due to one important CPU security policy. The policy says that in user space, the I/O operations and changing memory or virtual memory registers is not possible. And we have a kernel memory is not accessible. So we have this privilege separation. The user space privileges versus kernel space privileges. In the kernel space, all instructions and accessing all memory granted. So this is providing us this separation, the separation of privileges. I got dropped out of session. Can you please explain what happens during validation? Actually, we lost a little bit time and we are behind, but basic is the cache of CPU, address translation cache of CPU. All entries are cleared, and so that new process will start from an empty cache, so that it cannot access the previous processes cache information due to security and so on. There are some architectures trying to get this process ID versus address space as the key, so that they can keep the previous one, but this is out of our current scope. So that the new process after context switch is going to have some cache misses in the memory operations in the early stage. So this is our privilege separation, the user versus kernel, and all computers hardware in the kernel and the user processes are jailed into this area of that is provided by the CPU, the user mode and kernel mode. And it's something good, because otherwise, what could happen? Any user can access any arbitrary block of a hard disk, for example. So users can directly write on hard disk because of this low-level I/O instructions, and using the SCSI modes, SCSI operations, and so on. I could have formatted a hard drive as in the user space, only sending a couple of I/O instructions. And this is something we don't like. Forget about direct index. We need to put this user-based security. So this user A cannot read that one and so on. And it can consume all of the user's resources. It can consume all of the memory. It can consume all of the CPU. The user space program can disable timer interrupt, so that CPU belongs to that user, and so on. So this is all possibilities. So that's why we have this separation of privileges. But so this is not possible. But we need a mechanism to make this one possible. And this is what we call the system call. So user asks kernel to do an operation. So it is like an operating system API. And this mechanism is very similar to interrupt. So it is, the thing is, all interrupt handlers put CPU into kernel modes. So I have one resource of interrupt, which is hardware, and I can put another resource for software interrupts. And this is a special instruction, syscall in 64-bit, Intel, trap in 32 bits. Intel, I can have this interrupt generated by software. What I need to do is put some integers in register AX, and then I execute the syscall. So syscall handler is another interrupt service routine, and which switches between the system calls. Okay, so let me just yes, in the user mode CPU, I can call this instruction, and it is only a limited instruction. I can call it, do nothing else but put some integers and put something on the stack. So this stack, integer will tell me which which system call I'm requesting, and the others are the parameters. I'm going to just, if you're interested, of course, I'm going to show you Linux system call table. Are you interested in? There's some. Source. So it is hardware dependent. In this folder, I have entry, and we have syscalls, and this is my code. This one, okay. In this directory, syscall 32, and it is a table. There are tools from this table. They generate this output, the assembler output, and then that assembler output is compiled into the binary. So read is 0, write is 1, 2 is open, and goes like that. Okay, so these are all your good operating, system calls. Shutdown. We have networking, fork, exit, IPC, change directory, get current directory, and it goes like that. If you are curious about how many are there, the number is so it is. So these are the compatibility ones, about 32. If there is a 32 binary is working in your system, those are working, but actual limit is this one. So from 0 to 335, we have 5 systems. By the way, this is not authentic. Dennis would remember that. Get file descriptors is something I added, okay, just for advanced Unix course. So this is the entry point, and from that entry point, we have the corresponding system calls are implemented in the respective folders in the system. So let me just show you. Get UID. Değilmiş. Göstereyim. Şuradan read'i gösterebilirim. Okay, so this is our read source code. Okay. Buldum. So this one is our read system call implementation, which calls cases read, and who does another. this one, this calls another one, and so on. It goes like that. Not black magic, it is just source code, okay? So these are the system calls, and what we call, when we go into the trap, it turns out into this. I can show you a couple of tricks that will, it's for fun. So this is, for example, some multi-thread application. There is a utility called strace. You can install in Linux. If you execute that, you will see this, which is the system calls that this command executed in your system. So you can analyze system calls better. If you provide -f, it is going to give you the thread system calls as well, not the main thread. So this way you can see what is really going on. It is all C. I always been with some ASM plus. So which is plus? I couldn't see it. It's all C. Linux, yes. There are assemblers. So this is the processes, the system calls. Actually, you can see in the assembler as well. So when you have a very simple, I don't have that simple code, but so okay, let us execute. Let us compile this code. I put this static on purpose. Just I would like to have no library interference, so it will be a large binary. So it will be almost 1 megabyte of a binary. And this binary, in this binary, you can have obj dump, if I remember. I'm not good at remembering things. Okay, so this is the disassemble of my program. Okay, and what it does. So let us try to find where are the system calls. If I am lucky, bazen yazıyorsunuz, çıkmıyor. Ondan sonra nasıl diye yapıyorsunuz. Okay, we catch one of the system calls here. Okay. So our system calls is, buradan anlayamadık. AX'e, RAX'e 0 read olsa gerek ama mesela başkaları da var. Okay, I believe this one. 9E, whatever it is the system call here. And so we have a couple of other system calls, a sequence of system calls, one after another. BA, EA, and so on, 27, and so on. So as you can see, your code contains many of the system calls. Yes, of course. Printf requires a system call, but it is not direct. So we have some buffer memory. So when you write something, it puts into buffer, and that buffer is large enough. It is calling write. So printf, between printf and write, there's some buffering. That can be either line buffered or regular buffered. If it's a file you're writing on disk, it is like 4K at least buffer. If it is terminal, it is by carriage return. Until carriage return, it is buffered. Scanf and many things that requires I/O getting some environment information, getting process ID, making inter-process communication, opening a socket, reading a socket, writing a socket. Malloc is a good question because it is hard to answer. Malloc is handled by libc. Actually, in all of those system calls between the user process and the operating system, there is a large binary that we call libc. In a Linux, it is GNU libc. And that binary handles most of the things. And most of the dirty operations of malloc, allocating tiny pieces of memory, shrinking memory when you deallocate, make sure that they do not corrupt your system and so on, everything is handled by libc. However, the libc requires memory, and the memory comes from operating system, and it is done by the operating system when libc grows in terms of pages. So you allocate hundreds of 8 bytes from the same page, but when you're out of memory, your page is not sufficient, operating system, libc asks operating system, or through a page fault, the operating system intervenes and gives memory. So the Debian package has dependency of libc, not only Debian package, but also everything that runs depends on libc, because it is like a wrapper of all system calls. But of course, there is alternatives. You can write your own libc as long as you feel confident about yourself. But since it is tightly coupled with the kernel in this area, this touching services, the system calls, you need you need to follow this hard implementation already done instead of writing your own. Yeah, removing libc is not a good idea. One of you are joking about that. Yes. Okay, so I'm behind what I would like to talk today, but we are out of time. Do you have any questions so far? libc, the library, main library that all programs compiled against. Any program works on a Unix-based system, in also Windows and so on. It is the main library, as printf, string. You are using this includes in your program. All implementations of those functions are in the libc. If you are not writing during compilation, for example, lm is in math library, but if you are not writing a library name and you are using a function that you didn't write, is coming from libc. Okay, I can cover the content, no problem. I can go faster later. stdio, C is a strange language. Yes, it includes the entry points, but actually it is done by the linker. So the idea is this one. Actually, this operation is a two-phase operation. So this one is called the object file. It is short and it doesn't contain anything, but it contains this external dependencies. So if you look into this programs, it will see that it is using this function call, this function call, this function call. So these are some function calls. It depends on that. And in order to compile, it needs those functions to be fulfilled. And during compilation, what's really happening is when you see this TO, actually there is a hidden libc here. You don't have to write it, but it is coming from the compiler. And this is called linking phase. And during the linking phase, I made an error. How it is possible? Okay, I did something wrong. I'm not sure. Use this now. Okay, I made the command line error, but the idea is when you compile this way, there's a hidden libc and it will fulfill all of the functions you need. Because I didn't say yes to Singe's question, so stdio includes libc. Actually, you don't have to use includes. The header files in C only gives you the function prototypes. It doesn't fulfill anything. The actual position that the function goes into the binary is during this linkage state. So is linker used at all when we generate single object code for single source file? No, just the object code doesn't have to need the libraries. Linker is not used. Linker is the last stage that compiles all of the object codes into the target executable, either executable with a main or shared library. Okay, in Windows Word it is DLL. If your binary has a main, the entry point, it is an executable binary, and both are the result of output of the linker. Windows is using some other name for its API, but actually it is POSIX compliant, so it is like a system call, but they have slightly different mechanisms. And the system calls, although POSIX compliant, there are also non-POSIX system calls in Windows as well. So it's also true Linux. In Linux, we have POSIX compliant calls and Linux specific calls. In order to call our own system, we need to inform compiler. You can use assembler just to create this system call is an Intel instruction. And in assembler, you can call that, or you can use this function. In Linux, it is provided, so it is for calling any system call with numbers. So this function expands into this, put this number in EAX and execute Syscall instruction. Okay, any other question? So please do not hesitate to ask your questions in the COV. So we have COV group, and it doesn't have to be course related. If it is OS related and the course content related, you can ask all of your questions over there. Okay. Thank you very much. I'm going to see you next week. Until then, bye-bye.